I have selected the topic of discussion, which is the properties of impeller of centrifugal pump. Based on my experience, the properties of impeller of centrifugal pump topic is very important as far as design and sizing of pump is concerned. As you know, the main properties of impeller are specific speed, head coefficient, and inlet flow coefficient. But do you know how there is a relationship among the specific speed, head coefficient, and flow coefficient? I have never seen in any books and journal, but in fact, I have developed these relationships through derivations, which I want to present in this video. So let's start to discuss about the properties, and we'll also see that how the relationships among these properties. I mean, there is a relationship between or among the specific speed, head coefficient, and flow coefficients. Impeller properties are very important and useful topics for design and sizing of centrifugal pump, and these properties are inlet flow coefficient, head coefficient, and specific speed. This is the first, that is inlet flow coefficient. Inlet flow coefficient is one of the properties of impeller, and this property of impeller relates about the flow handled by the impeller. The more the inlet flow coefficient, the more the impeller has capacity to handle the flow. Impeller having larger inlet flow coefficient has inlet blade height larger as compared to low inlet flow coefficient impeller. Inlet flow coefficient is defined as the ratio of inlet actual flow, and the product of tip speed and circular area of outer diameter of impeller. So inlet flow coefficient phi is equal to Q in upon pi by 4 d2 square into U2, and impeller outlet tip velocity U2 is equal to pi d2 n upon 60, or there is another way through which we can express U2 is equal to pi d2 n rps, where phi is the inlet flow coefficient in constant, Q in is equal to inlet actual flow in meter cube per second, U2 is impeller outlet tip velocity in meter per second, D2 is outer diameter of impeller in meter, N is speed in RPM, and N RPS is speed in RPS, that is revolution per second. The second property is head coefficient, and head coefficient is the property of impeller which relates to the hydraulic head rise of the fluid. Higher the head coefficient, impeller can generate higher head flow hydraulic head. This implies that for the same diameter, impeller having larger head coefficient can generate more pressure than impeller having a smaller head coefficient. Outlet impeller blade angle decides the head coefficient. If impeller has outlet blade angle closer to radial, such impeller will have higher head coefficient. Similarly, if the outlet blade angle is larger, measured from the radial, which is away from the radial, in this type of impeller, head coefficient will have lesser value. So head coefficient is defined as the ratio of hydraulic head and the product of half and square of outer tip well speed. So head coefficient psi is equal to hs upon half into u2 square, where psi is the head coefficient in constant, hs is hydraulic head in joule per kg, u2 is impeller outlet tip velocity in meter per second. The third property is a specific speed, and it is a combination of inlet flow and hydraulic head. So higher the specific speed indicates the impeller can handle larger inlet flow compared to impeller having a smaller specific speed. Inlet blade height of such impeller is larger in case of larger specific speed. Using a specific speed, speed of impeller is calculated based on the design inlet flow and design head or pressure. A specific speed is defined as the ratio of product of speed and inlet actual flow to the power half and hydraulic head to the power 3 by 4. So specific speed NSP is equal to NRPS into Q in to the power half divided by HS to the power 3 by 4, where NSP is equal to specific speed in constant, NRPS is a speed in revolution per second, and HS is hydraulic head in joule per kg. Now a specific speed is expressed as speed NSP is equal to NRPS to the to into Q in to the power half upon HS to the power 3 by 4. If you put all these units, you will see this value comes as a constant. So a specific speed is a constant, unit is constant. Now multiply 60 on both sides because we need to convert the NSP into revolution per minute. So a specific speed NSP into 60 is equal to 60 into N RPS into Q in to the power half upon HS to the power 3 by 4. But N RPM is equal to 60 into N 60 into N RPS. So a specific speed NSP into 60 is equal to N. Now 60 into N RSP is replaced with N to the power N into Q in to the power half upon HS to the power 3 by 4. So specific speed NS is equal to NSP into 60, and specific speed NS is equal to N into Q in to the power half upon HS to the power 3 by 4. So value of a specific speed NS based on the speed in RPM will be 60 times of the value of a specific speed NSP when speed in RPS. Although specific speed has unitless, but its value depends on the unit of inlet actual flow, hydraulic head, and speed. That means if the unit of any quantity or all the quantity changes, value of specificity will get changed. Now this is the derivation for the relationship among the inlet flow coefficient, head coefficient, and specific speed. This is very important relationships which I want to present because I have never seen such relationship in any books and journals. So let's assume the following. Impeller outer diameter is D2 in meter. The speed of impeller in N RPS, that unit is revolution per second. Inlet actual flow is a Q in meter cube per second. Hydraulic head HS is joule per kg. Inlet flow coefficient phi is a constant. Head coefficient psi is a constant. So impeller outer tip velocity U2 is equal to pi d2 n rps is a revolution per second. Sorry, U2 is in meter per second. So pi d2 n rps. Now a specific speed nsp is equal to n rps into q in to the power half upon hs to the power 3 by 4. Now let us rearrange. So nsp is equal to n rps into q upon pi by 4 d2 square into u2 bracket close complete to the power half divided by hs upon half in u2 square bracket close complete to the power 3 by 4 into bracket start. This value is written again on top side to cancel it out. So pi by 4 d2 square d2 square u2 to the power half upon this has to be written again. So half into u2 square bracket close to the power 3 by 4. So this is written for this and this is written for this. So but we know the inlet flow coefficient phi is equal to q in to the power pi by 4 d2 square u2 and head coefficient psi is equal to hs upon half u2 square. So replacing this we can write NSP is equal to NRPS to the power phi half to the divided by psi 3 by 4 into, now we have to rearrange this, pi by 4 d2 square u2 to the power half divide by bracket stand half into u2 square bracket close to the power 3 by 4. Now further rearranging, NSP is equal to phi half pi to the power half divided by psi to the power 3 by 4 into, now then NRPS is brought down inside, that is it becomes a square, so pi square now divide by pi written here, so pi square upon 4 pi NRPS to the square d2 square u2 square to the power complete power half upon half u2 square bracket 3 by 4, but u2 is equal to pi d2 NRPS, so we can write NSP is equal to phi to the power half upon psi to the power 3 by 4 into u2 power 3 by 4 upon u2 to the power 3 by 4 into bracket start 1 upon 4 pi to the power half divided by half to the power 3 by 4. So further we can write NSP is equal to bracket start 1 by bracket start square root of, that means pi to the power half into to the power 1 by 4 bracket close into phi to the power half divided by psi to the power 3 by 4. By putting all this value, it is coming as NSP is equal to 0.474425 into phi to the power half in divided by psi to the power 3 by 4. Now multiplying NS is equal to 60 into NSP for speed in RPM. So NS is equal to 60 into 0.474425 into phi to the power half divided by psi to the power 3 by 4, which is NS is equal to 28.4655 into pi to the power half divided by psi to the power 3 by 4. So we have now two relations, one for a specific speed when RPM in speed in RPS. So you can use this, and when a speed in RPM you can use this, where phi is constant, psi is a constant, but a specific speed will be, if you use this, the flow will be in meter cube per second and head rise will be joule per kg. If you use this, a speed will be in revolution per minute, flow will be in meter cube per second, and hydraulic head rise will be joule per kg. So this is very important relationships among the specific speed, head coefficient and inlet flow coefficient. Now we have another relationships we can derive. A specific speed in another unit, a specific speed, a specific speed ns is equal to n into q in to the power half upon hs to the power 3 by 4, where n is speed in revolution per minute rpm. Hs is, now head rise hs can be written in another form, hs is equal to gh, where g is acceleration due to 9.81, it is acceleration due to gravity in meter per second, and h is in meter. So ns is equal to n into q to the power half upon gs to the power 3 by 4. So ns is equal to n into q in to the power half upon g to the power 3 by 4 into h to the power 3 by 4. So we can write ns is equal to 1 by g to the power 3 by 4 bracket close into n into q in to the power half upon h to the power 3 by 4. So ns is equal to 1 by g to the power 3 by 4 into ns minus 1, or we can write ns minus 1 is equal to g to the power 3 by 4 into ns. So where n s1 n s minus 1 is equal to, after putting this value, which is coming at 5.543 into the ns. So a specific speed ns minus 1 is equal to n to the n, where n into q to the q in to the power half upon h into 3 by 4. So h in meter, so ns is when n in rpm, q in meter cube per second, hs in joule per kg. When ns1 is n in rpm, q in meter cube per second, h in meter. And there is a relationship between a specific speed in ns or a specific speed n and ns minus 1. So which relationship you want to use? If you want to ns, use this relationship. You want to use n minus 1, you have to use this relationship. Now there is another way through which also we can express. So again, general equation for specific speed is ns is equal to n into q in to the power half upon hs to the power 3 by 4, and we can write ns is equal to n into bracket start 1000 divided by 1000 into g into h into q in to the power half. Since 1000 cancel out, gh is extra, so we have to write below gs into half into hs is already there 3 by 4, but we can write ns is equal to n into density of water is 1000, so this is density of water, divide 1000 into g into h into q in complete power half upon gs to the power half into hs to the power 3 by 4. But power is equal to density of water kg per meter cube into g into h into q divide by 1000, so unit will be kilowatt. So we can write ns is equal to n into p is power half divided by gs to the power half into gs to the power 3 by 4. So ns is equal to 1 upon g to the power 5 by 4 into n into p to the power half upon s to the power 5 by 4. So ns is equal to 1 by g to the power 5 by 4 into ns2. So ns2 is equal to g to the power 5 by 4 into ns, or after putting this value ns minus 2 is equal to 17.361 into ns. So a specific speed ns2 is equal to n into p to the power half divided by s to the power 5 by 4, where ns is equal to n in rpm, q in meter cube per second, hs in joule per kg, and ns2 is n in rpm, p in kilowatt, h in meter. And this is only for water application. Other formulas can be used for any other fluid, but if you want to use this correlation, then this is valid for only in case of water. So thank you and hope you have enjoyed the discussion about properties of impeller for a specific speed, head coefficient and flow coefficient. An interesting part is the relationship among them and how they are derived. And second is also how they are related when you change the unit of either head coefficient, either you change the unit of head, or you change the, from the flow to the power, how these are related and how the unit getting changed. So I hope you like this. Thank you. Thank you for watching.